Hey everybody, welcome to the video for section 3.5, Uniform Motion Applications. Check the description of the video for some links to sections of the video dealing with each of the examples in section 3.5. Here we go. Alright, uniform motion problems all deal with the formula distance equals rate times time, or D equals RT. Give you a simple example of that formula. Say we're driving down the highway at 60 miles per hour and we're driving for 3 hours. How far would we go in that amount of time? To get that, you'd multiply 60 times 3 and you'd get 180. So we would go 180 miles in 3 hours if we were going 60 miles per hour, right? Okay, so for this first example, it says an express train and a local train leave Pittsburgh to travel to Washington, D.C. The express train can make the trip in 4 hours, and the local train takes 5 hours for the trip. The speed of the express train is 12 miles an hour faster than the speed of the local train. Find the speed of both trains. So our textbook gives us a couple of hints, a couple of tips to make this process a little bit easier. The first one is to draw a diagram like you see here, and the second one is to make a chart and fill in the information in the chart like you see there below the diagram. So I went ahead and copied those two things out of the book over here to this presentation, and that's what we're going to use to kind of go by. So first of all, you're going to see the diagram here. We have everything spelled out. We've got the local train here in red, traveling for 5 hours. We don't know the distance, so we're just going to kind of leave that as distance for now. And then the express train, 12 miles an hour faster than the local train, and it's only traveling for 4 hours. So I've went ahead and put that information into the chart. Time, 4 hours for the express, 5 hours for the local. And we're going to try to fill in the rates for each one of those, and then we're going to talk about this column over here, the distance, as we go. All right, so the rate for we'll start with the local train. Do we know how fast the local train was traveling? Do we have any information about that? The answer is no. So this is algebra after all. So for rate for the local train, we're just going to fill in the variable r. We don't have any clue about it, so we're just going to leave it as r. The express train, it says, was traveling 12 miles an hour faster than the local train. So for that one, we're going to base our rate off of the local train, which is r, and we're going to make it r plus 12. It was going 12 miles an hour faster than the local one. The local one was r, so it's going to be r plus 12 miles per hour. And then to get the distance is rate times time, so we're going to multiply those two things together. For the local train, it's just 5 times r, so that's 5r. And for the express train, it's 4 times r plus 12. All right, at this point now we have to find out some relationship between what's going on in these two things, the express train and the local train. And actually what's happening here is that they're traveling the same distance. So that means that their distances are equal. So what we can do is we can set those two distances that we just created, that 4 times the quantity of r plus 12 and that 5r, we can set those two distances equal to one another. So that'll say 4 times the quantity of r plus 12 is equal to 5r. We've created an equation. We have one variable, r. We can solve for that r by following the rules of solving equations. So all we have to do is distribute. Get all our like terms on one side by taking away 4r. And by doing that, we have our solution, which is r equals 48. Remember, rate stood for miles per hour. R stood for rate in miles per hour. And so that means we just solved for the speed of the local train. Remember, the problem said to find the speed of both trains. So the local train was traveling at a speed of 48 miles per hour. And since we know that the express train was going 12 miles per hour faster than that, that means the express train was going 48 plus 12, or 60 miles per hour. And that's all we have to do. I'm going to double check just to make sure I've solved the equation correctly. I have. Double check, make sure that I've answered the question being asked, which was find the speed of both trains, and I've done that. So that's it for this one. Okay, here's another one of these uniform motion problems. This one says that Christopher and his parents live 115 miles apart. They met at a restaurant between their homes to celebrate his mother's birthday. Christopher drove 1.5 hours, while his parents drove 1 hour to get to the restaurant. Christopher's average speed was 10 miles an hour faster than his parents' average speed. What were their average speeds of Christopher and of his parents as they drove to the restaurant? So again, we set up a little picture here with Christopher on one side, his parents on the other, and then they're going to meet in the middle for lunch. So remember, they're 115 miles apart, so there's that part of the story. He starts over here, drives toward them. They start over there, drive toward him. Of course, he has to go a little bit further, and he's going a little bit faster. So just like the last one, we set up a little chart. Some of that information is already filled in, but that's the information from the problem. He's traveling for 1.5 hours. They were traveling for 1 hour. They went a total distance of 115 miles. Christopher's parents' rate, we don't know anything about. We don't have any clue. So we're just going to use the variable x for that. And then we know that Christopher's rate was 10 miles an hour faster than his parents, so we can relate his speed back to theirs using the same variable x and adding 10 to it. And then, of course, to get distance for each one of those, we just multiply the two things together, rate times time. So for Christopher, it's going to be 1.5 times the quantity of x plus 10. And then for his parents, that's going to be 1 times x, or we can just say x if we want to. And then to solve this one out, again, we have to come up with some relationship between the two things. And in this case, Christopher's part of the trip, or his distance, is only part of the drive, only part of that 115 miles, and then the rest of that 115 miles is his parents' distance. So basically what we can do is we can just add together those two distances, and we will get 115. So we can set the equation up like that. So it's going to look like this: 1.5 times the quantity of x plus 10. That part of it, remember, is Christopher's distance. That whole thing represents his distance. And then we can add his parents' distance, which was just simply x. We don't know anything about it. So parents, learn to spell parents' distance. We know the sum of those two distances is 115. This problem told us that. Now we have an equation with one variable x. We can solve for it. First, I need to distribute 1.5. Combine like terms, so 1.5x plus x is 2.5x. Subtract 15 from both sides. Divide by 2.5. And x is equal to 40. What does that tell us? That tells us that his parents' speed was 40 miles per hour. So parents' speed is 40 miles per hour. And then Christopher's speed is x plus 10, or 40 plus 10, so he was going 50 miles per hour. Let's go back. Let's make sure we've solved our problem correctly. We've answered the question. Average speeds of Christopher and his parents as they drove to the restaurant. That's what we were looking for. That's what we found. And that's it. All right. Very similar problem. Very similar methodology here. A little bit different story. The two truck drivers are going away from each other to different destinations, but that's irrelevant. The only thing that we're talking about here is how far they both drove. So it says 2 truck drivers leave a rest area on the interstate at the same time. One of them travels east, the other one travels west. The truck traveling west travels at 70 miles per hour, so that's this blue line here, west. And then the truck traveling east has an average speed of 60 miles per hour, so it's going over here at the red line. And it says, how long will they travel, or in other words, what's their time in hours before they're 325 miles apart. So, again, if we set up our diagram, in my opinion, it's pretty clear to see what we're going to do here. We've got a total distance of 325. We need to simply find the expressions that mean distance for the westbound truck and distance for the eastbound truck. Add them together and we get 325. So let's do that. We know that they were traveling different speeds, but there's only one time, right? There's only one time. It's the amount of time it takes them to get 325 miles apart. So the amount of time that they drive is the same. So we can use the same variable, t, to represent both of their times, because that number, whatever it is going to be exactly the same for both trucks. And then the distance for the westbound truck is 70 times t. The distance for the eastbound truck is 60 times t. And we know that if we add those two distances together, we get a total of 325 miles. So 70t plus 60t equals 325. Once we've got it set up, this is probably the easiest one to solve. Just add together your like terms. Divide both sides by 130. And we get t to be 2.5. 2.5 what, you might say? 2.5 hours, I believe, since time is in hours. And that is the solution to our problem. 2.5 hours is how long they will travel before they are 325 miles apart. Okay, for this one, let's talk about the story first. It says, when Katie Mae walks to school, it takes her 30 minutes. If she rides her bike, it takes her 15 minutes. Her speed is 3 miles per hour faster when she rides her bike than when she walks. What are her walking speed and her speed riding her bike? So the first thing we have to look at here is the fact that we're talking about speed in miles per hour, but we're talking about time in minutes. That's a little issue we've got to take care of. So the first thing we'll want to do is go ahead and convert those times over to hours. That way everything will be in terms of hours. So for 30 minutes, that's half an hour. We can write that as 1/2, or we can write it as 0.5. So for walking 30 minutes, I'm just going to change that to 0.5 hours. And then for the biking 15 minutes, I'm going to change that to 0.25 hours. For 15 minutes, that's a quarter of an hour, 0.25 hours. And of course, if you get something odd like 7 minutes and you're not really sure, all you have to do to convert that is just do 7 divided by 60, and that'll give you how many hours that is in decimal form. And of course, 7 divided by 60 is 0.116 with a repeating 6, so that's going to be about 12 minutes. Or rather, sorry, about 0.12 hours. It's not 12 minutes at all. It's 7 minutes. It's about 0.12 hours. So if we needed to convert 7 minutes into hours, that's how we would do it. Ignore the fact that I messed it up the first time. Okay, so from here, we need to set up our little chart. I purposefully didn't put the chart in the book here because we're not always going to have that. So sometimes we have to kind of create our own chart. So here's walking. Here's biking. We have 3 things. We've got D. We've got R. We've got T. We know that R times T equals D. So there's our equation. Let's go ahead and fill in what we know into the chart. We know the times. We know that when she was walking, it took her half an hour, or 30 minutes, or 0.5 hours. And we know that when she's biking, it takes her 0.25 hours. We know that the rates, we can compare the two. We don't know how fast she was going when she was walking. So it was x for the rate there, but we do know that she was going 3 miles an hour faster than that when she was biking, so we're just going to put x plus 3. And then, of course, we can set up our distance expressions by multiplying those two things. 0.5x for walking, 0.25 times the quantity of x plus 3 for biking. And then, what do we know about the distance? Well, if we look at the lines up there in our picture, we can see that the lines are exactly the same length, so I think we could probably assume that it was the same distance from home to school, whether she was walking or biking. So again, we can set those two distances equal to one another. And we can then solve that equation. So to begin with, we'll distribute. We need to do 0.25 times 3, and that'll give us 0.75. From there, we'll need to get all of our x's on one side, so I'll take away 25x from both sides. And decimals, when working with decimals, especially ones like this, we can think about it like we would think of money. We've got 50 cents, we take away 25 cents, we'll be left with 25 cents. Fix that, 0.25 is equal to 0.75. And if we've got 75 cents and we want to divide it into quarters, should be 3 of them. So x is equal to 3. So it looks like to me that she was walking at a rate of 3 miles per hour. She was biking at a rate of 6 miles per hour. So she's walking at 3 miles per hour. She was biking at 6 miles per hour. It said she was biking 3 miles an hour faster than she was walking. And look back at her question, what are her walking speed and her speed riding her bike? That's what we solved, that's what we found, so we're finished. Alright, ladies and gentlemen, last example here. Hamilton loves to travel to Las Vegas, 255 miles from his home in Orange County. It doesn't say California, but I was going to say Orange County, California. On his last trip, he left his house at 2 p.m. The first part of his trip was on congested city freeways. At 4 p.m., the traffic cleared, and he was able to drive through the desert at a speed of 1.7 times faster than when he drove in the congested area. 1.75 times faster, so we've got to think about that. He arrived in Las Vegas at 6:30 p.m. How fast was he driving during each part of his trip? So again, there's the picture. You can see what was going on. The first question I have is how long was he driving in the city? Looks like from 2 p.m. to 4 p.m. that'd be 2 hours. How long was he driving in the desert? That'd be from 4 to 6:30. That would be 2.5 hours, 2.5 hours. And then let's just go ahead and set up our chart with what we know and what we don't know. So, same kind of thing here. Here's city driving. Here's desert driving. I'll set it up a little bit backwards this time and put the rate and time over here. Rate times time equals distance. That'll give us a little more room for the distance part. Okay, so city driving. We don't know his rate, but we do know his time. Desert driving. We don't know the rate, but we do know the time. We have a clue about the desert driving. We don't have a clue about the city driving, so I'll let the city driving's speed be x. Desert driving speed, it says 1.75 times faster, so that's 1.75 times 1.75 times x. Set up our distance expressions. 2x for the city. 2.5 times 1.75x for the desert. And then how can I relate those two things? Well, I know that if I add them together, I get a total distance of 255 miles. I said this once before, but I'm going to say it again because I think it's important to repeat. When we're talking about distances here, when we talk about these two expressions, you have to think about those two expressions as if they mean one number. So the top number, 2x, that's one number. So if I knew what x was, I'd just multiply it by 2, and that would give me that number. And same thing down there. If I knew what x was, I could plug it in, and that would also give me one number. So the city driving number is 2x, and the desert driving number is 2.5 times the quantity of 1.75x. And if I add those two numbers together, I get 255. So to make sure I stress that point. So there's my equation. 2x plus 2.5 times the quantity of 1.75x is equal to 255. So if I multiply those two things together, or distribute that one item, I will get 4.375x bring down everything else, combine like terms. 2x plus 4.375x is 6.375x. And of course, to finish it out, I need to divide both sides by 6.375. And what do you know? It goes evenly. It goes 40 times. What did I find? I found the rate, or the speed, he was traveling in the city, which is 40 miles per hour. So city, 40 miles per hour. And he's going 1.75 times faster than that when he was in the desert. So for the desert, if I multiply 40 times 1.75, I'll get 70 miles per hour. Alright guys, that's going to take care of it for section 3.5. And I'm out. Have a great day.